Welcome to Instrumentation and Control channel. In this video you will learn all about magnetic flow meter. Be patient. Watch the video from beginning to end. In next 15 minutes you will be able to learn all about magnetic flow meter theory and practical. In this video you will learn magnetic flow meter working principle, sizing, different types of excitation method, cross-sectional view, different type grounding, industrial application, industrial looks, dry and wet calibration. High school physics tell us that a conductor passing through a magnetic field will generate a voltage that is proportional to the speed with which the conductor is moving. You might recognize it as Faraday's law of magnetic induction. In the case of a magmeter, the liquid itself is the conductor, and the magnetic field is created by coils placed around the pipe. Two electrodes placed on opposite sides of the pipe perpendicular to the liquid flow, and the magnetic poles measure the induced voltage. The voltage generated is proportional to the velocity, which is then converted to a flow rate. The liquid flow, magnetic field, and line between the electrodes form the X, Y, and Z axes. Figure 1 goes into more detail about the actual construction. Magmeter users appreciate how the interior surface of the device can match the upstream and downstream pipe diameter, and how there are no obstructions into the flow stream. The flow meter itself must have an insulating lining, which can be made from rubber, Teflon, ceramic, or other materials capable of standing up to erosive or corrosive media. Magnetic flow meter construction is very straightforward. The magnetic flux field, B, is generated by a coil that is mounted perpendicular to what are typically two electrodes. They will pick up the induced electromotive force, voltage. The magnetic field generates an electromotive force proportional to the magnetic flux density, B, the velocity of the conductor, V, and the diameter of the pipe, D. Magmeters are highly scalable, running from 0.1 inch to 104 inches or more in diameter. They work well for clean fluids, such as water, acids, and caustics, or in heavy particulate applications, such as paper stock, pulp, and lime slurries. As mentioned earlier, the main requirement is the process media must have some level of conductivity, with a typical minimum range of 1 microsiemens to 5 microsiemens. As long as the process meets this requirement, the meter should perform satisfactorily in the application. Most oil-based liquids are not conductive, which knocks magmeters out of many refinery applications. From the theory you came to know that Magflow work on conductivity of fluid. Minimum conductivity should have 1 microsiemens to 5 microsiemens. From this table you can select flow meter size versus velocity. You can select a magmeter according to velocity. Three type of excitation method used in magmeter to excite the magnetic coil. They are AC excitation method, DC excitation method, dual frequency excitation method. Since their introduction in the 1950s, magmeters have evolved enormously from a technology standpoint. A typical meter from the first decade would have used AC to excite the coil, so it used the available electrical line frequency of 50 Hz or 60 Hz. Users soon found the high sampling rate this frequency offered to be particularly well suited for noisy slurry applications, and it offered fast response to changes in flow rate. However, Users also noticed these AC-powered magmeters did not have a stable 0 point when there was no flow, if nothing was moving in the line. The devices tended to wander. They also used a large amount of energy, with many units drawing as much as 300 watt. As magmeter technology advanced, the next generation excited the coils with pulsed square wave DC operating around 6.25 Hz to 11 Hz. This worked well enough in most situations and delivered the sought-after zero stability. But lower excitation frequencies could not handle noise caused by a high solids content. The low sampling rates also made them sluggish when responding to rapidly changing flow rates. As new power supply circuits developed, instrumentation designers had more options available to try different excitation frequencies. This led to adjustable sensors where a user could choose the best frequency for the application. If the process is noisy with slurries or flow rates change rapidly, the user chooses a high frequency. For an intermittent process, such as a batch application with periods when flow stops, the user chooses the low frequency. This approach works, but as transmitters got smarter, it was possible to incorporate circuitry capable of using both frequencies simultaneously. Dual-frequency excitation allows the transmitter to superimpose two frequencies on top of each other at the same time. A low-frequency component of 6.25 Hz and a high-frequency component of 75 Hz work together for higher performance than either one functioning alone. Installation procedure, in upstream 5D and in downstream 2D. Grounding plays an important role while install Magflow. Wet calibrations that check the entire flow measurement system are generally not an option in most applications because challenging the installed flow meter with a known volume of water is impractical, especially in large pipes in remote locations. Even removing the flow meter to perform a wet calibration in a flow laboratory can be expensive and time-consuming. Further, it does not take the installed piping into account. On the other hand, dry calibrations verify the operation of only part of the flow measurement system. In the case of magnetic flow meters, a traditional calibrator checks the transmitter by verifying that a given millivolt input produces the correct flow rate. What if the wiring is faulty? What if the coil has changed its characteristic? What if the flow tube leaked and shorted an electrode? Dry calibrations do not necessarily check for these problems. Now you are ready to go. Thanks for watching. Please like, subscribe to motivate and for upcoming new videos and put your notification on.